Here is a simple trick which you use, for instance, to evaluate contour integrals. Very often you come across an integral like a to b dx over, let us say, a less 0 less than a less than b, positive numbers. So, square root of b minus x times x minus a to do this integral. This is a simple definite integral and the answer is very well known. But you can do this by contour integration using a little trick, and that is the following. Consider the function 1 over square root of z minus a times z minus b. Okay. We know how to draw cuts for this function, z minus a to the minus half, z minus b to the minus half. So you can draw a cut between a and b, and that is it, and write the phases of this function down, etc. What is meant by this integral is an integral over positive integrand, a positive integrand. This is the modulus of this function here between a and b. So what you do is, and I am going to leave this as an exercise, you consider this function, choose the cuts, the cut to run from a to b, write down the phase here, write down the phase here, arrange it so that the phases are known here and here, and then I already showed that across a square root branch point the discontinuity is just twice the modulus, and the reason is on one sheet it is modulus, on the other sheet it is minus the modulus. So exploit that, apart from factors of I and so on, which you must be careful about, to convert the line integral from a to b to a contour integral of this kind. So a line integral, I have exaggerated here, a line integral from a to b, a line integral from b to a in the opposite direction coming down, but it is a different function there because there will be a sign change, and then two small circles around these. Consider this contour, this is a closed contour. I have come back to the original value because I have not crossed any cut at all. Now what is this value equal to? Well, this part of it can be related to the original integral I, apart from some factor. This fellow can be related also to minus I, it is going in the wrong direction. So the whole thing will be proportional to twice I, this part and this part, but you have added these little pieces out here. We have to ask what happens to these little pieces, but now what happens near z equal to b, for example, on this circle z is equal to b plus epsilon e to the I theta on this circle, and what you are doing is integrating from pi to minus pi, and out here you are integrating, when you come down here, from 2 pi up to 0 in this fashion. But look at what happens to this function here. You have a dz on top and there is a z minus b here. This fellow is harmless. In this factor you could put z equal to b if you are in the neighborhood of b. In this factor you have to put z minus b is epsilon e to the I theta. This dz is going to give you an epsilon e to the I theta, I d theta. There is a power of epsilon here and there is a power of square root of epsilon here. So the net result is a power of square root of epsilon on top, and what happens to that when epsilon goes to 0? It vanishes. So similarly this portion also vanishes, and now what has happened is that your original integral, this real integral, it is a real number, is apart from some factor of 2 pi or 2 pi whatever it is given by this closed contour, but this function has no other singularities. So you can rewrite that closed contour like this or the other way, whichever. You can blow it up, you can blow it all the way up to infinity. What happens when z goes to capital R e to the I theta? This goes to R e to the I theta I d theta, and this guy here a and b become irrelevant, and you get exactly the z downstairs too. So the r's cancel out and you have an integral over d theta from 0 to 2 pi, which will give you a 2 pi. So the value of this integral actually turns out to be equal to 2 pi. and you have done this without any special tricks, changes of variables or anything like that, simply by choosing the branch points appropriately, branch cuts appropriately, and it is exactly equal to 2 pi, and using Cauchy's theorem once again. We did not even evaluate a residue in this case. Notice that I cannot write this contour by crossing this, I do not cross this branch point at all. If I do, then the function has changed and I have to compensate for it, I have to do something else. There is another closed contour possible in this case, but that does not give you this integral, and that is this following. I go around this once, I pick up a factor 2 pi, in this case a minus 2 pi, but I could also come back and pick this up. So I go around this way, I get a plus 2 pi, and they will cancel each other since they are both square roots, and that is a closed contour. There is a cut here, but that is fine, because the function has returned to its original value. And if I were to rewrite it in this form, what I am doing is the following. I start here, I go around like this, I come here and I go around like this and join it in this fashion, in the opposite direction. We will play with contours of this kind quite a bit, but after you gain a little practice with the phases of these functions, it is quite straightforward to do this. You can already begin to guess that I have used A and B here. Had I used 0 and 1, then there would be branch points at 0 and 1, and if you recall the definition of the beta function, there was a singularity at t equal to 0, 1 at t equal to 1, and I am going to exploit this sort of feature in order to write a contour integral representation for the beta function eventually. Okay. But I hope this little trick of doing these integrals with a little practice, we will do a little more, a few more of these. This is an extremely useful way of doing things. There is one more integral which also one can do, and those are integrals of the following kind. Very often you end up with an integral of the form dx and then some p of x over q of x, where p and q are polynomials such that for this trick to work the degree of q must be at least 2 or more greater than the degree of p, for a reason which will become clear. So let us say these are polynomials, p and q, such that degree of q minus degree of p is greater than or equal to 2. And we also require for this trick to work that this integral be well defined. In other words, there should be no zeros of q of x which are real, no non-integrable zeros of this thing. So no real positive zeros. These are assumptions. So when you have an integral of that kind such that q has no real positive zeros, no singularities on the region of integration, line of integration, and the degree of q is at least 2 or more greater than that of p, then this integral can be done in a very quick way by using contour integration with a little trick, and the trick is the following. So consider the following integral over a contour C, which I am going to prescribe now, dz p of z log z divided by q of z. Okay. And the contour is the following. In the z plane, this function log z that I have introduced has branch points at z equal to 0 and z equal to infinity, right. So it has got a cut which I choose from here to there, and out here the function is log x on top, and out here it is log x plus 2 pi I, because the argument of z has increased by 2 pi I. And now consider this contour, a hairpin contour which comes along like this and goes off to infinity. That is my contour C. Okay. So it does not cross this branch cut, that would take me to a function which has a different value in another sheet. So I am on the principal sheet of this log, but the contour is a hairpin contour which goes just below the real axis on the principal sheet, goes round the origin and goes off to infinity once again. And what is this integral equal to? This thing here equal to an integral. Now look at what happens at the origin. There is no singularity at the origin, that this quantity in the limit will go to 0, because what happens here is that z is epsilon e to the I theta, and you have a dz which has an epsilon in it. This fellow here will have a log epsilon, but epsilon log epsilon, the limit goes to 0 as epsilon goes to 0. So it does not contribute at all, this fellow. I have added this and then I expanded it out. And then from here to there is the integral 0 to infinity dx p of x log x over q of x. That is from 0 to infinity. I have taken the limit epsilon goes to 0 here, and then this integral is infinity to 0 in the opposite direction plus an integral from infinity to 0 dx p of x. That is single valued, it is a polynomial, so it does not change anything, log x plus 2 pi I divided by q of x. Okay. So let us call this integral that I want, let us call it I, and I have considered this contour integral. What is this equal to? Well, this is equal to this infinity to 0, I convert to 0 to infinity and put a minus sign out here, and miraculously the log cancels out, the log integral cancels out on both sides, and I have a 2 pi I times the integral that I want, which is I. Okay. Right. And now the next step of course is obvious. What should be the next step? So I have reduced the integral that I want to this contour integral, but to do contour integrals you have to close the contour without crossing any cut. So what should I do? I draw a huge circle and close the contour. Well, technically I should keep it to some capital R, let the limit R go to infinity and so on, but this is essentially what I do. I must ensure that this large circle that I drew, the contribution from that is 0 in the limit as R tends to infinity. But that it is, because you got a capital R from here, you got R to the degree of P, and then the log is irrelevant, and you got this R to a degree which is at least 2 more than that. So it takes care of this dz R also, because the degree of Q is twice or 2 or more greater than the degree of P. Not 1 or more, 1 or more would be a problem because there would be an R from the dz, but it is 2 or more. So in the limit it goes to 0. Pardon me? There is a minus sign, there is a minus sign somewhere, yeah, minus, right. So now we are in good shape, because this immediately says that this integral I equal to minus 1 over 2 pi I contour integral, and it is a closed contour now, dz p of z log z over q of z. So you introduced a log z gratuitously, but that has helped us to do the integral, reduce it at least to a closed contour. What next? Where are the singularities of this? Well, there are branch points here, but they are outside the contour. I can now shrink this integral, and there would be singularities, there would be all the poles of the zeros of q of z. there will be some poles because it is a polynomial and we assume there are no poles on the positive real axis, no zeros on the positive real axis. So these are sitting somewhere else and they are inside the contour now, and they are all being enclosed in the positive sense. So this guy here is equal to minus 1 over 2 pi I times 2 pi I summation over the residues, residue P of z log z poles at the zeros of cubes. Okay. But there is a log sitting there. So you can do a large number of integrals with this little trick. For instance, you could do this integral. You know that you can do 0 to infinity dx over x squared plus 1. This is trivially done. This is a tan inverse something. But suppose you wanted to do x cube plus 1 or x to the n plus 1, n greater than or equal to 3, some positive integer. Suppose you wanted to do this integral. This has got singularities or zeros at all the roots of x to the roots of the equation x to the n is minus 1. So write this as e to the 2 pi ri, the one, and then put an e to the I pi because of the minus sign, and it has got singularities at various places. For instance, if n is 3 for example, then x cubed is minus 1 and the roots are at minus 1, something here, something there. And all you have to do is to pick up the contribution from these poles with the appropriate logs and simplify, and that is the answer. Okay. There are other ways of doing this, but this will tell you this is independent of how what the power here is. It's straightforward to do this. Okay. So certain integrals can be done using this. This is a simple example of how you exploit this logarithmic branch point in order to actually evaluate definite integrals. Okay. What we need to do next is to ask if some of the special functions we talked about earlier, like the gamma function and the beta function, have representations that go beyond the representations we found by integrating by parts or special tricks of that kind. And recall, the first one we will do is the gamma function. So recall that gamma of z was defined as 0 to infinity dt t to the power z minus 1 e to the minus t, and the caveat was that the real z, the real part of z had to be strictly positive. Okay. Then the singularity at the origin did not bother you. Okay. Now I would like to continue this analytically using a contour integral representation. And the trick is the following. The trick is, in the t plane, this integrand for general complex values of z has a branch point at t equal to 0 and at infinity, and we choose the cut to run from 0 to infinity. What is the phase of this function t to the z minus 1? By the way, this fellow is an entire function, no problem at all. What is the phase of t to the z minus 1 just above the real axis on at t? 0, because the phase of t is 0, right. So the phase here is 0, and what is the phase here? Not z but t, t increases by pi. So what is the phase here? 2 pi z, 2 pi z. Why do not I bother about the minus 1?
The extra 2 pi z.
This becomes e to the minus 2 pi I, and that is 1 of course. So all that I am saying is that t to the z minus 1 equal to mod t to the power z minus 1 above, and it is equal to mod t to the power z minus 1 e to the 2 pi I z minus 1 below, and this one is gone because it e to the minus 2 pi I is 1. So the phase is 2 pi z, that is all I have written down here. Out here it is pi z. Now what is the contour I should consider? I want to convert this to a contour integral. What is the contour I should consider? Exactly the same contour. So I consider this guy here, this hairpin contour in this fashion. I call that C. Okay. And let us see what the integral over C is. So integral over C dt t to the z minus 1 e to the minus t is equal to an integral from epsilon to infinity, and I am going to write the limit epsilon goes to 0 right away. So this is 0 to infinity dt t to the z minus 1 e to the minus t. By this I mean a line integral from 0 to infinity, the original gamma function, plus an integral from infinity to 0. So this is from infinity to 0 dt, again t to the z minus 1, and by t here I mean a positive number, the range of integration being what it is, times e to the 2 pi I z out here, because that phase comes from this factor here, plus a contribution from this circle, but on this circle t equal to epsilon e to the I theta. So the contribution from that circle is of the form an integral from 2 pi to 0 epsilon e to the I theta I d theta, that is dz dt t to the power z minus 1. So you got epsilon e to the I theta to the power z minus 1 e to the minus whatever it is, e to the minus epsilon e to the I theta. There is an epsilon here and there is an epsilon to minus 1 here. So those two fellows cancel out, and you are left with an epsilon to the power z. But what does that do when epsilon goes to 0? It goes to 0 provided real part of z is greater than 0, otherwise it is not true. But that is where we started, that is where we started. So in this region this has gone, and the contour integral is equal to 1 minus e to the 2 pi I z gamma of z in the region real z greater than 0. Okay. So it is a delicate argument. We keep real z greater than 0, and then what I have shown you is that this hairpin contour is equal to 1 minus e to the 2 pi I z times gamma of z. So this implies that in this region this is also, gamma of z is also equal to 1 over 1 minus e to the 2 pi I z integral over the contour dt t to the z minus 1 e to the minus t in that region, point by point. This is where the poles of the gamma function arise from, because you can write this as sine whatever it is. Pull out an e to the I pi z and then it is minus 2i sine pi z in the denominator, and that is where the poles would come from. But you see, once you have done that, then you can distort this contour. So here is the branch point, and I can write the contour like this, going off along the real axis to infinity. Can I now close this? Can I do that? No, no, because this function is bad news. This fellow is bad news. It will not converge. If I open it out, you can open it up to a certain point, but it is not going to help much. real z must go to plus infinity, otherwise that integral will not converge. So I leave it like that, I leave it in this form. But the point is, the important point is, does the contour touch z equal to t equal to 0 anymore? No. And the problem with negative z to the left of real z equal to 0 arose because of what happened to the integrand at t equal to 0, but now the contour does not touch t equal to 0. So you put any value of z you like and the integral still makes sense. So this is valid for all z. And it is an analytic continuation. So let me go over the argument again. You started with this and showed that in that region this line integral could be written as this contour integral. They were equal point by point for every value of z. But the contour integral makes sense, it converges for all z. So it is a representation of the gamma function. And you can now read out what the singularity structure of the gamma function is from this directly. We know from other considerations that the gamma function has simple poles at z equal to 0, minus 1, minus 2, etc. with minus n, the residue is minus 1 to the power n over n factorial, and it has no singularities for positive integer values of z. It is in fact the factorial. That should show up here, that should show up here. What happens if I put z equal to a negative integer including 0? What happens to this branch cut? Suppose t is z equal to minus 3, then you got dt over t to the power 4 e to the minus t. What sort of singularity does that have? It has got a pole, it has got a pole at t equal to 0. Is there a branch cut? Is there any multiple valued function left? No. So the branch cut disappears, the discontinuity disappears, and you have a pole at this point and you have a contour of that kind. You can now, since there is no discontinuity, you can join these two and this becomes equal to at this pole, and that is 2 pi minus 2 pi I times the residue at that pole. This will give you a simple pole at z equal to minus n because it is a sign in the denominator. You must be careful to write the residue, it has got pi factors and so on, and this fellow here will also give you factors when you evaluate the residue at the origin, and that is not hard to do. What you need is a coefficient of 1 over t. So suppose this is t to the minus 4, you look at the coefficient of t to the 3 here, and that gives you a 1 over t, and that is going to be 1 over 3 factorial, right, or whatever. So it will also give you, straight away it will give you the residue minus 1 to the power n over n factorial. Minus 1 to the n comes from expanding e to the minus t, and the n factorial comes from the expansion of e to the minus t. So this will recover for you the fact that the gamma function has simple poles at negative integers, non-positive integers z. But we also know that when z is a positive integer, this function is regular, it is n minus 1 factorial. That should show up too, and that is tricky, because if z becomes a positive integer like 6 for example, you have dt t to the power e to the minus 5, and there is no cut here at all and no singularity here at all. So in the limit that integral vanishes, and it vanishes and kills the 0 of this function at z equal to a positive integer such that the ratio of the two tends to n minus 1 factorial. Okay. So the fact that the gamma function is just a factorial at positive integers will also come out, but it is a little harder to establish. You might as well establish it from here directly by integrating by parts, but this will no doubt give you the right answer also. But it happens because the cut disappears, but the pole also disappears and the contour integral vanishes in the limit, and it vanishes, so does the denominator, and the ratio is finite. But for negative integers, this contour integral does not vanish, it just picks up the residue of the pole at 0, and this gives you a simple pole and it gives you the right residue at this point. Okay. But for other values of z, this is a representation. For arbitrarily large values of real z on the positive or the negative side, does not matter, it is still a representation. Okay. So if you like, this thing here is a master representation a sort of master representation from which you can write down the value of gamma of z for all z. But typically it is an integral representation, and the important thing to remember is in this instance you cannot open this contour out, you can't do that. Okay. This is the best you can do. It is useful in many ways. So we will try to derive a similar representation for the beta function, and let me take that up next time.